crystal field splitting, octahedral splitting, tetrahedral splitting. Transition metal chemistry is dominated by d electrons that can occupy 5 d orbitals. The crystal field theory, or CFT, is an electrostatic model. Ligands are treated as point charges or dipoles. As the ligands approach the central metal ion, a negative electric field is created and the degeneracy of metal ions d orbital is lost. For a free transition metal in the absence of any crystal field, the 5 d orbitals are degenerate, which means they all have the same energy. In octahedral field, 6 ligands are coming towards the corners of an octahedron, causing the central metal or ion orbitals to have different energies. In an octahedral field, 6 ligands approach, 2 along z-axis, 2 along x-axis and 2 along y-axis. What happens to the energy of the d electrons if negatively charged ligands are brought in towards the metal center to give an octahedral complex? Since the d electrons are themselves negatively charged, they would experience repulsion from ligands and their energies would be raised. The degree of repulsion depends on the orientation of the d orbitals. In an octahedral crystal field, we say that d orbitals have an octahedral energy splitting, and we denote this by a delta with subscript O. 3 orbitals of lower energy are represented by T2G set and 2 orbitals of higher energy are represented by EG set. Complete the d orbital splitting in an octahedral field by dragging the respective orbitals as indicated. In tetrahedral field, 4 ligands are coming in at the corners of a tetrahedron, causing the central metal or ion orbitals to have different energies. In tetrahedral field, imagine 4 ligands are lying at alternating corners of a cube to form a tetrahedral geometry. These 4 ligands approach along opposite corners of a cube, forming a tetrahedral crystal field. dz square orbitals is lowered in energy as it lies in between the ligand and experiences less repulsion. dx square minus dy square orbital is lowered in energy as it lies in between the ligand and experiences less repulsion. dxy orbital is raised in energy as it points towards the ligand and experiences more repulsion. dxz orbital is raised in energy as it points towards the ligand and experiences more repulsion. dyz orbital is raised in energy as it points towards the ligand and experiences more repulsion. In a tetrahedral crystal field, we say that d orbitals have tetrahedral energy splitting, and we denote this by a delta with subscript T. 2 orbitals of lower energy are represented by EG set and 3 orbitals of higher energy are represented by T2G set. Complete the d orbital splitting in a tetrahedral field by dragging the respective orbitals as indicated.